Start. Okay, hello everyone, good afternoon. Welcome to our Maths&Stats Seminar. So today we have Tim from the University of Waikato, if that is pronounced correct, and he will talk about the ample DR-Semigroups.
Thank you. Yeah, it's nice to be here again. This is a talk I gave last week, and I'll be giving again next week, but I'm going to add on some extras at the end because we've got a bit of extra time, so that's good. Also means I won't have to rush through this first half. So just to remind you, of course, you're all going to know what this is, but semigroups are just a non-empty set with a binary operation. I'm not going to use any particular symbol for it, so I'll just use juxtaposition. There's the associative law, which they satisfy. And of course, semigroups are rather different from groups in one key way, and that is that in a group, you only have one element like this, an idempotent element. I won't tell you what it is. But in semigroups, they're quite important in determining the structure of the semigroup, and they're going to feature in this talk. And they have a natural order on them. You can easily check this is an order, a partial order. We just say that one idempotent is below another if this pair of equations holds here. E equals E, F equals Fe. There's no requirement that EF equals Fe in general, but we do require it if E is going to be below F. And it is, in fact, a partial order. It's a nice little exercise to check that. Now, the things I'm going to talk about are what I'm calling DR-Semigroups. And these are semigroups where we have a sort of a domain-like operation and a range-like operation. When you're thinking of things having domains and ranges, you're thinking functions, you might even think categories. And that's a good thing to think about because I'm going to try and show that this is part of a bigger project which has been going on for decades of showing that you can view certain semigroups as basically just categories in disguise. And this is good in a way because you can throw away almost all the products. Just remember some of them, along with maybe some extra information like partial orders, maybe only one partial order, and then you can reconstruct the entire semigroup from there. So that's the basic philosophy here, and I'm going to apply it in a case that's a bit novel here. So here's what a DR semigroup is. Basically, you distinguish a set of idempotents E, which is going to be such that it may not be all of your idempotents, but such that there's the smallest member of E under the natural order. So given any S, there'll be a smallest E, such that it acts as a sort of a left identity for S. So it's like a smallest left identity within big E of S. And we'll call that D of S, sort of like the domain of S. And similarly on the other side. So smallest has to be under the natural order. That's the order I defined a minute ago. And these were defined in this level of generality about 10 years ago. That these ideas have been kicking around for a while, but typically in the past it had been assumed that the idempotents formed something like a semilattice. So you assume that you had commutativity of the idempotents, but turns out there are a lot of nice examples where that doesn't hold. So it turns out also that with D and R defined in this way, they're basically unary operations. By assumption, they're defined for all members of the semigroup. We can view E as being just the image of either one of them. So in a sense, if we know D and R, we can get E. And in fact, there is a nice axiomatization of these things just in terms of the semigroup operation D and R. And here it is. You assume you've got a semigroup, first of all, and it just has two unary operations satisfying these things. And it's relatively straightforward to verify all these things do hold for DR semigroups, but it turns out it characterizes them in the sense that if you have a bi-unary semigroup satisfying these laws, you can just define E to be the set of all domain elements, which turns out to equal all the range elements, and D and R will be exactly as I just described them in the definition a minute ago. They'll be the smallest left and right identities of elements within E. So that's nice. You can view these as just an equational class. So just these are finite number of equational axioms involving the D and R and semigroup operation. And often that's what people will use this as a starting point. but I think it's kind of nice to motivate it with a sort of order theoretic definition. And there are a lot of examples where the elements of D of S may not commute with one another. So, but on the other hand, for this, at least for the first half of the talk, I'm just going to assume that they do. There's also a huge number of examples where they do. So in other words, I'm going to assume that if we have two elements of our E, which remember now we can write as D of S, that they commute with one another. And I'll give some examples pretty soon. And it follows, by the way, that they then form a sub-semigroup, which is a semilattice because it consists of idempotes that commute with one another. So that's what we call a semilattice. And we'll call those the projections of S. And I may or may not use that term again. I forget whether I do, but it's safer to define them. So the projections of S will be these elements in D of S or R of S or the original E, if you prefer that way of thinking about it. Now, a particularly important class of DR-Semigroups, remember I'm just assuming EF equals FE always now, is so-called Ehresmann semigroups. These were defined, I guess, by Mark Lawson in the early 90s. And they do just happen to satisfy two more laws. And these are called the congruence conditions. And they look like these two things. They look slightly arbitrary laws, but there's a real reason why these are chosen. Now, a restriction semigroup is a special kind of Ehresmann semigroup, so it satisfies the congruence conditions and a couple of other laws. And it's kind of hard to take these laws in without any context, but these are called the ample conditions. And there seems to be an arbitrary domain element appearing here, but we can write that as D of Y, and then this just becomes two equations. We can think of those as sort of universally quantified equations if we want to. So it basically says that this law says that if we have an element followed by a projection, we can write it as a different projection followed by the same element. You can flip projections over, but they'll change. And in fact, they change according to this formula. Actually, it's enough just to say for all x and e, there exists an f such that xe equals fx, and then it forces, you can always pick f to be this, it turns out. So I could have expressed it differently, but given this more sort of equational description. So anyway, I haven't said anything about where these things come from yet. Let's do that. If you know about inverse semigroups, then these will give a nice supply of these things. So take your inverse semigroup, which is the nearest thing to a group within semigroup theory. You have this notion of generalized inverse. And in an inverse semigroup, you assume that they're unique. So what's the generalized inverse of S? It satisfies these things here. And if you additionally assume that every element has a unique generalized inverse in this sense, you get what's called an inverse semigroup. The idempotents end up all commuting with one another. And if you make these definitions here, remembering that this thing's uniquely determined by S, that determines D and R, it gives you a restriction semigroup, which is one of these DR semigroups satisfying both these conditions here. But if you just want an Ehresmann semigroup, and I've got one of those too, take all the binary relations on a set, much more general than inverse semigroups in a sense, where you're basically modeling one-to-one partial functions on a set. That's the standard example of an inverse semigroup. If you take all binary relations instead under composition of binary relations, which is just a generalization of composition of functions, then you get, if you take D and R to be defined in the following way, you'll get an Ehresmann semigroup. Now, what are D and R? You take a binary relation rho, you take all the x's that are in a domain of it, so you think of it as a set of ordered pairs, the binary relation's a set of ordered pairs. The first coordinates are the members of the domains. That is the domain. All the things that are related to something else in the forward direction. And on the other hand, R of rho is defined dually. We just use the image or the range of rho instead. We turn it into a binary relation by just restricting the identity function to the domain and the range. Turns out to be a useful, natural thing to do. And it kind of agrees with this one up here. If you take the symmetric inverse semigroup of all one-to-one partial functions then these two things are just exactly this in that case. And indeed, if you restrict to the one-to-one partial functions, you get a restriction semigroup because you actually get an inverse semigroup. We know they give restriction semigroups. All right, so there's a bit of a supply of these things. Now, back in 1991, Mark Lawson showed how you could view any Esmond semigroup as a special kind of category. And you've got a nice correspondence between Esmond semigroups and this class of categories. And this actually generalised an earlier result for inverse semigroups, known as the ESN theorem, which I think Lawson gave it that name. Esmond, Shinen and Burapad viewed them as contributors to this theorem, which is one that related to inverse semigroups rather than Esmond semigroups, one being a more general version of the other, basically. One difference is that the inverse semigroups have inverses, so they're a bit more than just DR-Semigroups, but still. Now, so how do you do this? How do you turn an Esmond semigroup into a category? First of all, what do I mean by a category? It's worth knowing what I mean by a category. I mean, everyone has a notion of what a category is, but algebraists typically define categories in a very efficient way. They don't bother about objects. Who needs them, really? You could do the whole of category theory without the objects ever being mentioned, because you can view as a category really as a kind of generalized monoid. And I'll view at least a small category, so we've only got a set of arrows. I'll view it as a set, a non-empty set, I guess, with a partial binary operation and two unary operations. And so there's no objects in sight here. Let's have a look later at how we introduce the objects. We can basically bring them in, but here are the laws. Now I've got these two unary operations, and you think of those as being the identities on the source and target of an arrow. And if you think of d of x as being the identity on the source of x, then of course this is going to happen. And over here, similarly with the r on the identity on the target. And of course, this is a basic property of a product in a category. And then we have a couple of other things that happen down here. And then the last one is a way of saying that the partial binary operation is what I'm going to call here a partial semigroup. Basically says that, let's suppose this product exists. Well, what do I mean by that? I mean, first of all, the Y circle Z exists, and then you can also do this longer product as well. If that product exists, so does this one. And that means, first of all, that this product exists and then the longer one does too. So that's all implicitly in there, that information. So these two things all exist together, and in that situation, they are equal. So it's a sort of associativity condition. Now, this is a very natural law, because if you take a semigroup with zero and just delete the zero, and then define your new operation on the resulting smaller set to be only partial, it won't be defined if the answer was going to be zero, but otherwise it's just what it was before, you get one of these partial semigroups. Conversely, if you start with a partial semigroup, just satisfying this law here, you can always just add one extra element corresponding to when it was undefined before, and you'll get a semigroup with a zero. So there's this nice correspondence between partial semigroups and semigroups with zero. And of course, you can do that in particular in a category, but it turns out that's not particularly the way we're going to think about things here. So other things follow. You can show stuff like this. If you apply D twice, it doesn't change the element. Applying R to D, again, doesn't change things. Similarly, dually. And we call the identities the elements of the form D of X or R of X. They're just like what I was calling the projections in a DR semigroup. But I'll call them identities here because this is a different kind of thing this time. Now, how does this correspond to the more familiar definition of a category where you have a bunch of objects and morphisms? Well, all you have to do to make this into a category in the way you may be used to is to just formally introduce an object for each identity. You can even make the identity the object if you want, so the identities will be the objects. That's a perfectly good way to turn it into a category with objects. But you really don't lose anything by throwing the objects away, because the identities basically pick them out for you anyway. So you can do everything purely algebraically that you could do with category theory. So that's what I'm going to call a category. So that allows me to move on, because when I show Esmond semigroups correspond to categories, it'll be in this particular algebraic way, with no objects. Anyway, how do we do it? How do we turn an Esmond semigroup into a category? Well, given the bit of the definition of a category that says this, there's a fairly obvious thing that we can do. So what we're going to do is just going to say, define x circle y to be xy, but only when r of x is equal to d of y. So that should have the required property back here. So automatically this axiom is going to be satisfied. If I keep the r and the d the same, define this new partial product, it'll obviously satisfy condition 2. And in fact, it satisfies the others. You can take my word for that. It's a fairly straightforward verification using the axioms. You do need to use the congruence conditions, not just the DR-Semigroup laws. Congruence conditions are needed to show all of the category laws work. Now, it would be nice if you could just forget about all the other products entirely, and somehow that remembers the entire category. If you think about the case of binary relations, imagine you've got a set with 1,000 elements. What's the chances that r of x equals d of y? It's vanishingly small. So we're just remembering a tiny fraction of the products. It's not surprising, therefore, that this thing on its own doesn't quite capture that semigroup. Most of the products, almost all of them, have been thrown away. Obviously, it's for an infinite set x, it would be literally a sort of set of measure 0. Anyway, this category doesn't capture the original Esmond semigroup, unfortunately. But we can remember, we can recover it all if we just define a couple of partial orders. Now, partial orders are still much more sort of efficient things than binary operations, because all you have to do is remember whether something's less than or equal to another thing. Probably isn't. So you just got a few less than or equals to remember, rather than the value of the operation in each pair. So it's still pretty efficient if we could just add a couple of partial orders, and that's enough to capture the whole Esmond semigroup when you combine it with the category. Turns out that is possible. So let's see how we do it. So here's one partial order. I'll call this domain restriction, because that's really what it is. S equals d of s times t. And I'll duly define range restriction like this. And these things turn out to be partial orders, and they're actually equal in restriction semigroups. I'll just mention that, by the way. These two things turn out to be equal because of that ample law. Lets you swap the projections over from one side to the other. That somehow forces these two things to be the same partial order. Okay, so I've got these two partial orders. Now, that actually, there's some other things we can say about these partial orders. They both, when you just restrict to the projections, it's just the natural order on the idempotents there. And they form a meet semilattice. And the meet is just multiplication. It's just the product of the two elements within D of S gives you the meet. So that's all quite nice. They both agree there, and they're equal to this natural order. So that's an observation we can make about the order. Here's another one we can make about the order. The two orders, actually. One at a time, though. So pick any domain element or projection that's less than or equal to D of S. Then we can actually identify products of this form, E times S, where E is less than or equal to D of S, because it's the unique element below S under this natural order whose domain is E. So that completely pins it down. All you need to know is what the order is. And then you can find it. It's the unique one. I'm not giving you an algorithm for how to find it, but it is fully identified if you know the partial order. Right? We know this information, and we can spot this thing that's below S. Its domain is E. And the same for S times F if F is below R of S. So products like that are captured by the information I've got so far. So I've thrown away almost all the products, but I've remembered two partial orders, and now I can get all those products. But on the face of this seems a long way from general products, but actually we're almost there, because we can write general products in the following way. Now, remember, this meet, we know that exists. It's an order theoretic thing in the projections, R of S meet D of T. Turns out that this is below R of S. Well, obviously it is, because it's a meet with something else. So I can do this product here, and I can identify this product using the order. Similarly for the one over here, same sort of argument. And it turns out that this is a well-defined category product. So the range of the left-hand side equals the domain of the right-hand side. So all this calculation is being done only knowing the category product and R and D and the two partial orders. Okay. And so all that information is enough to somehow recover the entire semigroup. And Lawson actually showed how you can even axiomatize the by-ordered categories that you get in this way from Esmond semigroups. So they are just another way of thinking about Esmond semigroups, categories with two orders satisfying a bunch of conditions. And he gave axioms for them. There's a nice finite axiomatization. It'll say things like, you know, for any S and E below S, there is this left restriction of S by E, and there's a right restriction as well, and some other properties. There's a finite number. You can write them down as properties and show that then you could recover an Esmond semigroup from them, construct one, and you get this nice one-to-one correspondence. You actually get an isomorphism of categories, the Esmond semigroups on the one hand, and these by-ordered categories on the other hand. In fact, Lawson called them Esmond categories for obvious reasons. Now, the thing that really made this work at the beginning is that you assume the congruence conditions hold. That allows you to show that this thing here with the restricted product I defined a minute ago is actually a category. That's the starting point. You at least want to know you can make a category out of your semigroup. Otherwise, you can't really get very far. What if we don't have the congruence conditions though? Because there's actually a lot of interesting examples that don't have the congruence conditions satisfied. Well, one observation we can make is that we can actually define the two partial orders I gave earlier, even in a general DR semigroup. Remember, I'm assuming that E times F equals F times E at the moment. So we can still define these. I do have to modify the definition a little bit, but it's not really modified. I have to say D of S is below D of T and S equals D of S times T. In the case of Esmond semigroups, this condition implied this one, but now I have to state them both separately. This will make sure that I get something that's equivalent to what I had for Esmond semigroups and still gives a partial order. And similarly for the other one, I'll define that in the obvious dual way.
Projections still commute.
Yes, I'm always assuming projections commute throughout the part of the talk that involves the slides. Yep. So yeah, absolutely, I'm assuming that. So these are partial orders. And they just, as I said, they give you the earlier definitions. If you happen to have Esmond, this part of the definition becomes redundant. That's because of the congruence conditions, otherwise it's not. All right, so that's a good start. We've got these two partial orders. Now, for restriction semigroups, it's an interesting thing that the two partial orders are the same. I mentioned this earlier, didn't I, that the two partial orders end up being the same for them. And that makes things a bit easier to do. You've only got one partial order, so doing all the workings out becomes a bit easier. And the axiomatization of, I don't think they're called restriction categories, that's something else. But they're a bit simpler to characterize than the Esmond categories. Anyway, we could just impose that. So I'll drop the congruence condition, but I'll keep the assumption that the two orders are the same. Now that seems like a bit of an arbitrary assumption, but what we have is this nice little theorem here. The two partial orders coincide on the DR semigroup if and only if it satisfies that ample condition. Now, this is something that's been known for Esmond semigroups for quite a while, but it's actually not much of a stretch to make it still true if you drop the congruence conditions. So, yeah, we're just going to be looking at the ample condition being assumed throughout. So, I mean, if I was to do a little bit of a drawing of the situation, the most general situation was DR semigroup here. And then we had Esmond. And then we had restriction. This is getting less and less general. And then the inverse, actually. In fact, we've also got ample over here, the ample conditions. If you combine these, you get this one. So this was the original ESN theorem applied to these. Then Lawson came along and did those. And by the way, he did these as well. And they're quite similar to these because there's only one partial order. Just easier. This one, that's what I'm doing today. We don't have the congruence conditions. What on earth happens? Do we still get a category? By the way, there's another reason to look at ample. It's a bit circumstantial, but it's kind of a weird thing. So all Esmond semigroups satisfy the following condition. If R of x equals D of y, then D of xy equals D of x and R of xy equals R of y. This guarantees that you get a category, actually, because this is one of the other key properties of a category, that if the product exists, then the domain of the product is the domain of the first one, the range of the product is the range of the second one. This exactly guarantees that. And Esmond semigroups satisfy this because D of xy is D of x D of y, which is D of x R of x, which is just D of x. And similarly here. So use the congruence conditions. Without the congruence conditions, this is no longer going to be necessarily true. Actually, it might still be, but probably won't be. On the other hand, and here's a weird thing, restriction semigroups also satisfy the converse of this condition. It's quite a peculiar thing, which looks like this. That if these two things are equal, then R of x equals D of y. And in fact, we have a little theorem that says, in the general DR semigroup case, yeah, that converse direction is true if and only if the semigroup's ample. Kind of weird. And I don't know how significant it is, but it's more sort of circumstantial evidence that ample is a natural condition. I'll say that much at least. So maybe there's good reason to look at ample. So let's try that. Okay, well, are there any natural examples of them though that are not restriction? Remember the restrictions, we've got plenty of those floating around. But what about ample ones that are not restriction? Otherwise, what's the point really? Well, I can give you a few examples. If you look at all the one-to-one partial functions on the set, you get a restriction semigroup because it's an inverse semigroup. But it's restriction. Can we tinker with that sort of an example in some way to stop it satisfying the congruence conditions? Well, yeah, there are a few things we can do actually. Here's one. Take X, your set on which you're defining your functions, to be the integers. Let's look at one-to-one partial functions. Okay, so we're in the direction of this. But I'm going to restrict them. I'm going to say that, and here I'm using application of functions on the right of their argument. So xf is like f of x. But I'm going to assume that xf is at least as big as x, but no more than 9 bigger. Obviously, you can replace the 10 here by your favourite natural number. There's nothing special about 10, but just for concreteness. And I'm going to define composition in the usual way, but of course, you could get a difference bigger than 10 if you applied 2 of these functions to the same argument. The first one might be 7 and increase, and then the next one increases by 5 and you're over your limit. So we'll just knock that out and leave the composite undefined in that case. So it's not really the composite at all, it's a modified composite. But obviously FG defined this new way will still satisfy the condition here because we knocked out cases that didn't. So it's closed, and in fact it'll be an associative operation, and we can define D and R on this perfectly well. That certainly satisfy this, xf equals x whenever it's defined actually. And this is a way of getting a DR semigroup that's ample but not Esmond. And I guess there's a bit of proving to do to show that, but you can trust me that it does work. This is And not a totally unnatural sort of example, I think, assuming a sort of bounded increase. Here's another one. Just take any old non-empty set with a closure operator on it. And then I'm just going to turn it into a semigroup. The subsets of that set I'll turn into a semigroup by making intersection the operation. This is a classic example of a semilattice. And then I'm just going to define D of an element of this, D of a subset of X, to be R of it, to be the closure of it. So you've made it a little bit bigger in general, according to the closure operator rules. Well, this is going to give us an ample DR semigroup that's not Esmond in general. It's unlikely that the congruence conditions are going to hold. Everything else is easy to check. So, of course, D equals R, so it's not a very typical example, but it's another very different sort of example. So there's a few of these floating around. If you want to get a totally new one, take a Cartesian product of this with another one. There are more examples you can get, by the way, and involving sort of a variance of categories and subsets of them, but I'm not going to talk about those now. Well, can we do this same sort of trick of viewing a DR semigroup as some kind of category in such a way that that category captures all the information in the DR semigroup that we started with? That would be nice if that was possible. Well, we can't quite do it actually, mainly because we can't make it into a category, but we can still discard most of the products, almost all of them, in the same sort of way as before, and get something category-like with some order information in there as well that captures the original thing. Let's see how that works. So let's think about an ample, I'm calling these ample DR semigroups if they satisfy the ample conditions. Now remember, this means that the two orders are the same. So we've really only got one order now. So that's made life a bit simple in the same way that these two ones were a bit simpler than this one. So we've got that going for us at least. There's only one order to worry about. I'm going to define X circle Y to be XY, but when am I going to define it to exist? When this happens. And remember, that implies that R of X equals D of Y. That was one of the things I just observed about ample DR semigroups. If these two things hold, then R of X is equal to D of Y. But that could happen without this other condition happening. So we might have R of X equals D of Y in an ample DR semigroup, but this condition here does not hold. So that means I don't want to make that my way of defining the product. Okay, so we have that. Now, this is what we get if we do this. Let's keep D and R, and now I'll keep this circle. It's not quite a category, because as I say, the product may not exist if R of X equals D of Y. So that was one of the axioms for a category. So if that's gone, then we can't have a category. But we've got something that is, in a sense, even more restrictive than a category, you could argue, because not only are we saying, well, we're saying that's not enough, it has to happen, but there has to be more on top of that for the product to exist. So we're still chucking away tons of products. What do these objects satisfy? Well, all the laws of categories I gave before, except that now R of X equals D of Y is only necessary for X circle Y to exist. It's implied by it existing, but it doesn't imply it. So we'll call these things that we get in this way partial categories. This is where the partial categories come in. All right, so actually Hitmar Stein introduced these thinking about representation theory of semigroups. He had a different thing he was thinking about. He was interested in, if you restrict the product on the semigroup and take the associative algebra on that restricted thing, when is it isomorphic to the associative algebra over the semigroup? And he was able to get some conditions for that to happen. Anyway, that was quite recent work, which I think is now in semigroup form. We also have available only in this one partial order. Remember, the two partial orders are equal in the ample case. So fine. Now, here's the trick that we're going to do. Remember the way that I had a way of writing any semigroup product before, which turned out to allow me to capture any semigroup product just using the order and the category product. I'm going to do something similar here. It won't be obvious at the beginning that it does it, But I can definitely, for any x, y, and s, I can write the product of x and y like this. Now, this is using my partial product that I just defined, which is the partial category product. This is a well-defined partial category product because the condition is satisfied. If you test it on these two things, you'll see that it passes the test for the partial product to exist. You can also see that it's equal to, what's it equal to? D of x, y, calculated in the semigroup. Well, okay, d of xy times xy, that disappears. Similarly, that disappears and we get xy. So there's no doubt that that's equal to xy if it exists as a partial product, but it does. You can check that in your own time. However, this doesn't look great because we've got xy on both sides. We've got an xy on the right. Earlier, we didn't have that problem. We just had xy on the left expressed in terms of things that were just purely order theoretic or category theoretic. Here I've got xy appearing still, so this doesn't look that promising. On the other hand, it turns out that's not a problem because we can characterize these two elements here totally order theoretically. Quite a nice fact. So for any x, y, and s, the x1 equal to this one and the y1 equal to this are the largest x1 and y1 respectively below x and y under the one order such that this product exists. So they're the largest things below x and y such that the product exists in the partial product. So we've completely captured them both in this order theoretic way with the partial product as well. So again, that means that that's all the information we need to remember. The partial order, the partial product, D and R are enough to give us everything, and we can recover the original. We can get arbitrary products in this ordered partial category. Now we still have to characterize the objects that we get. There'll be some kind of partial category. By the way, one way to get these partial categories is as certain subsets of categories which are not generally closed under the composition, so that you get a product that's restricted even relative to the category product. That's why they're called partial categories, but I don't think they all arise that way, but that's the typical way you can get them. Anyway, we're going to get our ESN theorem here. We just have to describe these objects up here. And just for your reference, here are the axioms for them. I'll just whiz them up. We get a partial category, we've got a partial order on monotonicity. D and R are monotonic. You've got this property which corresponds to one of the things we had back there. Some other things here, and then that. Anyway, it's a finite axiomatization which completely captures these partial structures, which is similar but different to the way you characterize Esmond categories. There you had notions of left and right restriction that you don't have here. And it turns out not to be a convenient thing to think about, but we get this other way of doing things. All right, that's just about the end of the first half. These are the references that I cited as I went through, if you're interested in chasing those up. And if you actually want to really chase this stuff up, pretty soon, I hope this will be in a certain journal. It's just getting its second look over after some revisions, but meanwhile, you can find it on the archive. So thanks. Now that's the first half, so contain your applause. I'm just now going to stop sharing and I'm going to use the board for the remaining time. So hopefully everyone can see the board now behind me. You wouldn't have been able to up to now. So apologies to those not in the room. These are all the things that I went through. There'll be some of you, but it wasn't too crucial, I don't think. All right, so let me carry on. Now, have I got it right? Great. Okay. All right, so now remember that at the beginning,
Before you rub that up, just a quick question.
yeah, sure. It's a good time.
DR-Semigroups, strictly speaking, sit between DR and Erison.
Yes, DRC are here. So In the case that I've looked at, though, they're the same as this. Because I've assumed DF equals FE throughout.
Yeah.
However, now that we've gone into chapter 2, yes, you are correct. So I'm now going to drop the assumption of EF equals FE on the projections. And this is a good thing to do because there are many examples of interest which don't satisfy that. As we know, there are things like bare star semigroups and regular star semigroups, star regular semigroups, and of course all the ones we had before. Now, most of those satisfy the congruence conditions still, to be fair, and any that do would be in this category here, DR-C semigroups. So they satisfy the C's for congruence. The congruence conditions hold for these. There's a nice ESN theory for those. It's more complicated than it is for the Easman case. You need a bit more data, but it's all just at the category and order level. And so you don't need to remember any extra products or anything, but there's just a little bit more to keep track of. Okay. But again, I'm going to steer away from these and towards cases that don't satisfy the congruence conditions in the general setting where this doesn't necessarily hold, and see what we can do. Now, what I'm going to do is I'm just going to define the partial product in a DR semigroup now, just a general DR semigroup where I'm not assuming the projections can be commute. I'm just going to define it to be that, providing the first half of the earlier, in fact, the exact same definition that I just used. In general, that will not imply R of X equals D of Y. You'd have to add that in as something extra. So this does not imply R of X equals D of Y in a general DR semigroup. In fact, in what I'm doing, it's almost never going to. However, we can still do something. Even just imposing this restriction is very severe in terms of the products that are left. All right. Now, what do we want? If I have these conditions here, then I've obviously got this. Which is a good thing. This is one of the significant parts of the definition of a category. It's just imposed by this assumption here. But, and I can even write this. This will exist using this operation here that I've just defined. But of course, these may not be meaningful anymore in a way that I can capture using orders or anything. So I have to be careful about how I can do this. I will note that we definitely have this. Different now. The projections have, actually, no, they've just got one order on them. And R of XY is less than or equal to R of Y. So we could, I suppose, view these as restrictions and left and right restrictions still, but they really terminally have XY in them, and there doesn't seem to be a nice fix in general. So in other words, for general DR semigroups, although we can do everything I've just said up to this point, we can't really identify these elements just using the two orders, which are now different in general. So what am I going to do? Well, what is satisfied? So this thing here, so S is my semigroup that I'm starting with. Under this partial product, D and R, Well, it obviously satisfies this still. Well, it's fairly easy to check it anyway. And of course, it'll satisfy these two as well. So that's well along the way to being something category-ish. What we'd really also like is to have this thing being a partial semigroup. Fundamental part of having a category. If it was a partial semigroup, with respect, then if I combine with these other things, I get something very close to what I define a partial category to be. The one gap is that just because a product exists, it won't imply that R of X equals D of Y anymore, but everything else there is going to be fine. So we'll get something very close to a partial category in the way to define it. It's nice to get a partial semigroup here if we can, because it's really just a semigroup with a zero missing. It's always good if you can knock out almost all products, sort of reset those products to be zero, and then you still got a semigroup, but it's got a zero that features it very often. Well, here's a nice little theorem. S circle is a partial semigroup if and only if a couple of algebraic conditions follow. S satisfies, as a semigroup, this is, Stein's generalized ample conditions. What are those? Well, they featured in his work on semigroup representation theory. I can just write down what they look like. It's not going to mean much, but they are just relatively simple algebraic conditions. Kind of interesting that they correspond exactly to this being a partial semigroup. And what they are is these. And I'm kind of getting bored with writing, so I'm going to say and dually. So you swap the role of X and Y, swap order, swap D and R, and you get another law. Looks very similar to that one. So there's two laws, one's to the left and the other's right. And then we will get basically a partial semigroup, except that just because the product exists, it may not imply that R of X equals D of Y. But it's pretty good. I guess it's a generalized partial category or something. All right. However, of course, that's all nice, but it doesn't necessarily mean that that resulting partial structure captures the original thing. So I could look at any S that satisfies Stein's generalized ample conditions, and then look at the partial products D and R. I could even try and remember the two orders. Just the approach done with Airsman and everything else I've been doing. This may not capture the original. We have to add in a little bit more. Now, these things, I haven't said anything about these yet because I haven't defined them in general, have I? But the definitions are exactly the same as they were, and it still works even if you drop commuting of the projections. So remember I defined S less than or equal to RT, if and only if S equals D of ST and D of S is less than or equal to D of T under the natural order. And similarly for the other one. That still works even if you drop commuting of the idempotencies. So it's what we use for DR-C semigroups, for example. And you don't even need the C part for it to work. So we still have these two partial, they are proper partial orders still. But as I say, you can't capture the original semigroup just from this data, even if you have enough information to say that this is a partial semigroup and it satisfies these other nice things automatically anyway. Pretty close to a category-like thing. So what am I going to do? Well, what worked before? I may as well keep the theme going from the first half. I'll assume that these two orders are the same. Well, that might give me something. Now, if I add the congruence condition in, I'll just get what are called DR-C restriction semigroups by doing that. Because these two orders are the same for DR-C semigroups if and only if you've got a DR-C restriction semigroup, which is a sort of non-commuting projection version of restriction semigroups. But in general, what we can say is these two things being equal is equivalent to the following conditions. And dually. So again, it's a funny thing. You can write down a couple of conditions. I'll call these, actually, is that Idmar's definition from before? That's not quite what I want. What I actually want is some weaker conditions. I think this is what I gave before, isn't it? Oh no, I think this is it. Yep, no, that's okay. This is different to the ones from before. Yeah, there's the one before. It's different, isn't it? Tell me it's different. It is. But it turns out that these two are implied by these two.
There's a missing parentheses. Is that meant to be after the X on the left-hand side?
I don't know. I think it's supposed to be here.
Okay.
It's actually missing there. You'd never know that. Thanks. Yeah. Yes, there's a D of X here and a D of X over here. That's right. Right, so this property, I call that balanced. It's just saying that the two partial orders are the same. It implies Itmar-Stein's conditions. That means we're in the world where we get a partial semigroup. So this thing here is a partial semigroup. And so we can hope to get something nice corresponding to these S's, providing we can actually capture all the products. And in this situation, where we assume the orders are the same, we actually can. So here's how we do it. We can write ST. Now remember, I can write it like this. So this is perfectly well-defined partial product. The problem was that these didn't seem to have an order theoretic definition. They did in the ample case I looked at when I assumed that EF was equal to FE, that the projections commuted. What about now? Because this is really the analogous position that we're in, right? We're assuming the two orders are the same. We just dropped this assumption. That's the only change. It's a pretty big change, of course. But what happens is we can characterize these orders theoretically, providing we introduce a projection algebra structure on the projections. Now, in the DR-C case, what you do is you take two projections and you define, there's different ways of doing this, but this is the way that's most often done, I think, except in the work of us. But you can define these two binary operations on projections. And you get what's called a projection algebra. Now, in the Asman case, these are just equal to EF. So this is just meat. This is product. It's the simulator's meat. But in general, in the DR-C semigroup, it's not that. Well, I can still define that here. And it turns out that this thing, this is going to be largest S1. Now, before, what was it? It was the largest S1 below S under the one order, such that, and this was the largest T1 below T under that same order, such that S1 circle T1 existed. Now, I'm going to have to change that a bit here. Comes the largest S1 below with this order, different one, two orders now. S times R of S star D of T over here. And we can think of this as a sort of right restriction of S. And then this whole thing is a left restriction of S. And this one is the largest T1 below the analogous thing involving T. This time we're going to have T and then R of a left restriction by an element of the projection algebra. such that S1 circle T1 exists. So this I haven't published yet, so it's not fully quality assured, but this is the generalization of what I talked about in the first half to the situation where you don't have that working anymore. Seems fine. So then I haven't got an axiomatization for these partial categories, but you can always get one in principle. You just say that when you define the obvious product, it satisfies all the things you want it to. So there's always an axiomatization. It's just whether it's an elegant one or not. You've always got a cheeky one like that. It's going to be finite. So yeah, there we have it. I'll probably stop there. I think we've got another speaker coming up. So thanks.
Any question for him?
Equal or admitted. There's the some projection times x is x times some other projection.
Yes.
But the two projections are quite specific.
Yeah, they're not that general, are they?
You can't replace it by saying ex equals x. Something.
Seems not. Yeah. As soon as you do that, you end up with this holding. It forces this. So if I use that DR-Semigroups laws from before, I would just end up with this being a consequence. So I can't. That's a good question.
So you can't just have it, but with the right-hand side projection is way more complicated. It's just
no. In principle, there's no way to do it. Yeah, that's right.
Is there any way to interpret those two projections?
Oh, this and this.
Yeah.
So far, that's all I know about it, that it works, yes.
Any other question? Is there any question online?